All right, sketching polar curves. Fun stuff. I like this. So, for these problems, remember our technique. What I want you to first do is graph the corresponding rectangular, corresponding Cartesian trigonometric function. So what I'm saying is graph the normal cosine function here, and then we're going to use that to help us graph the polar curve. So, how are we going to do this? Well, let's think about how this function works. What does that 2 do, that constant term? Well, that is shifting our graph up 2. So let's draw some axes here, and let's go ahead and say 2. 2 is right there, and I'm going to dash in a line showing the axis of symmetry of this cosine graph. What does that 6 do? Well, that 6 is the amplitude, which means above that axis of symmetry, we will go up 6, so that's going to put us up at a maximum of 8. And we would go below that axis of symmetry by 6 as well, so that's going to put us down at negative 4. At that point, it's just a cosine function, which we have had ample practice graphing. Notice we have not modified our period at all, which means if we break it up into 4. So what I was saying before I got cut off was that we're going to split it up into our 4 pieces. Again, labeling our pi over 2, our pi, our 3 pi over 2, and our 2 pi, which of course correspond to these 4 nice, easy to use values around the unit circle. Now at this point, we're just talking about a cosine graph, which we know cosine here starts at its maximum value. So we're going to start our cosine graph at its maximum value, and then cosine is 0, which would put us on the x-axis, but we have that plus 2, so we're down on our axis of symmetry. Negative cosine value corresponding to that minimum there, then back on the axis there, and back where we started. So again, just running through the cycle like we should hopefully know it does. Now, the whole idea here is we're going to use this graph to help us sketch the polar curve. So I've created this little polar coordinate system there with our different radius rings, aka concentric circles, going out, and the angles marked 0 all the way up to 2 pi in increments of pi over 4. And I made this on GeoGebra, and it is very nice and pretty, and GeoGebra is super awesome. So what do we want to do now? Well, we're going to use our graph over here to help us graph this polar curve. And so we're going to use it essentially as a set of points, r's and thetas. So we have our r values on our vertical axis, and then our theta values on the horizontal axis. So let's look at our first theta value and go all the way to 2 pi and see what happens. Well, when theta is 0, the radius is 8. And so I'm going to go ahead and put my first point right there. I have 8 rings. That is my 8th radius out there, and I am along the theta axis of 0. So there's my first point. Next easy point I can look at is this one right here at pi over 2. My radius is 2, and so I can plot that point right there. So I know I'm going to somehow curve in like that, but I want to make it more precise. So I want to figure out where I am at pi over 4. So at pi over 4, halfway between, let's figure out where we are. How can we find that r value right there? Well, we can plug in our theta value of pi over 4 to this equation. So 2 plus 6 times the cosine of pi over 4. That's going to give us 2 plus 6 times cosine of pi over 4 is the square root of 2 over 2. And so we need to figure out what this value is. It's fine if you want to use a calculator for this part. You just need to make sure that you're in the proper mode, either radians or degrees. It doesn't make a difference, you just need to input the correct angle value. Because if you type in 2 plus 6 cosine pi over 4 and you're in degree mode, you're going to get 7.999, almost 8. And then your graph is going to be incorrect, because that value is actually 6.24. So we're about 6 1/4 there at that spot, 6.24. And so then let's use that value over here along our pi over 4 line. 1, 2, 3, 4, 5, 6 1/4. It's going to put us about there. It gives us just a better idea of how we're getting from the 0 point to our pi over 2 point. All right, well, let's keep going. Our next easy value is pi, and we have a negative radius there, which means if you find the pi line, which would be going out that way, since our radius is negative, we actually need to go the opposite direction. So 1, 2, 3, negative 4 is actually over there. And I know it's kind of confusing at first until you get the hang of it. So we have this like awkwardness where we know we're going up and curving down like that, but then how do we get to there? So again, let's check a point in the middle. Let's check 3 pi over 4 right there. If that was pi over 4, here is 3 pi over 4. And let's figure out where we are. And actually, we don't really have to use a calculator again at this point, because we know whatever distance this was above the axis of symmetry, we are going that same distance there below the axis of symmetry. And so how far did we go? Well, that point was 6.24 above 2, so that distance was about 4.24, which means we're going to be going down 4.24 from 2, which means we're going to be at about negative 2 and a quarter. So at 3 pi over 4, we're actually down here. And so this, another important piece to talk about here, is the fact that we cross the axis there where the radius is 0, which corresponds to the pole right there. So think about this nice smooth curve going up, curving like that, coming down, crossing the pole, hitting that, and curving out to that point, because that is what we're dealing with right there. Now think of the significance about where we are right now. We are halfway through that cycle from 0 to 2 pi. We're at pi. And the cosine graph at this point is just going to repeat everything in the opposite order. So we're going to do this exact same spiral out, and we're going to get perfect symmetry. But let's make sure we do. Let's check all these points again. If we go to 5 pi over 4 right there, I know that this point is going to have the same r value as this point right there, negative 2.24. So if I'm at 5 pi over 4 and I'm negative, I'm actually up there. Perfect symmetry so far. Notice again, we're going to cross the pole right there, and then we're going to go to that special point, 3 pi over 2. It's going to have a radius of 2, and so we're going to get that point right there, and this is going to curve up, cross the pole, and hit that right there. Continuing through, again, let's check this value, 7 pi over 4. We know that that value will have the same radius as that value right there, 6.24. So at 7 pi over 4, we have 6.24. 1, 2, 3, 4, 5. 6.24 is right there. Again, notice perfect symmetry with the 1 above it. And then finally, cosine function is going to end right where it started, back at its maximum value. And so we end back at this same point. So we can continue this curve down. That looks bad. And there you have it. We have a limaçon with an inner loop. Now think about the values here that gave us that inner loop. We have a maximum R value here of 8. That 8 came from 6 plus 2. We have an inner loop value here of 4 right there, coming from 6 minus 2. We have these special pieces right there at 2, coming from that 2 right there, and it's a cosine function which starts at its maximum out here, so we started there. So a lot of symmetry and pieces you can use and recognize to make sketching these a little easier in the future. But there you have it. It is our limaçon with an inner loop. To get an inner loop like that, notice we have a coefficient that is greater than the constant value. 6 is greater than 2. So if you're thinking about this as r equals A plus B cosine theta. We have this ratio A over B, and it is less than 1. That will result in a limit solvent with an inner loop. And there you go.